Hi, good evening. This is Wen. This is the last minute tutoring on your latest homework number 5. I know I shared a video earlier, but I thought that some of you may benefit from additional video that go through steps in greater detail. Okay. First, I want to offer thank you for all of you who've been trying so persistent on this particular assignment. And I know that this is not a very easy assignment, but I do hope that your understanding is improving even a little bit. Okay, so I'm hoping that this additional video can be a form of encouragement for all your efforts. I know that we talk about this in class. Struggling is not a bad thing. It's actually very natural. It'll be very strange that if you didn't struggle in this particular assignment. Okay, but if you want to be respected or even be recognized as some career professional who knows something that other people do not know, I think the statistics is something you can never overlook. Okay, so if you look at some of the this is Toledo Public Library archive. So if you look at, there's some of very interesting books in your public library. So if you think that things are interesting, getting interesting, and if you want to know more, but not using Wen's perspective, rather using something more layman's perspective, you can go search statistics from the Toledo Public Library, and there are some pretty good resources listed down here, especially something like the cartoon introduction of statistics and the art of statistics. There is some depth in this book, and Stat 101, the naked statistics, and so forth. So there are a bunch of resources that can help you run down the road. I just want to convey that information to you. With that, let's quickly jump into our assignment. Okay, so there is a characteristic. There's a common characteristics in all these problems. Number 1 and number 2 and number 3. Okay, so all of them are using sampling distributions to drawing conclusions. Okay, drawing conclusions about whether we should, whether we should put trust on the null hypothesis or not. Okay, so that is the reason why we spent some time earlier trying to distinguish between the population distribution and the sampling distribution. Okay, with that, let's starting from the problem number 1. If you have completed number 1 already, please take a look at the timestamp information in the description below, and you can jump into the next question if you believe that you have completed question number 1 satisfactorily. Okay, let's take a look. So I believe you have already studied this, so I'm not gonna go over the question again. I have data here. I explained how did I arrive these labels. And now I'm going to draw my sample. I forgot the sample size. So 36, right? 36. So I'm going to go here and random. No. Sampling. I'm going to input this range. There's a label. Let's go to 36. Okay. Output here. Okay, so this is a bunch of flags, okay, flags about whether you have drawn a sample that is defect or not. So what is my sample? The proportion defect in my sample? This is the P bar, which we are going to be using to make a decision about this, the hypothesis, okay? To quickly calculating the proportion in this case, when things are being measured using 0 or 1 fashion, and the fastest way to calculating the proportion is basically average the range here. Okay, then close it. Boom. So in my case, my defect proportion is 17%. You may have different results, but you need to make sure that you have drawn sample from this defect column. Okay, from this defect column. This defect column tells you whether this observation is a defect or not. This is your sampling result. So in my case, that was 17%. So with that, let's go back to the question. So I'm going to put okay, 1667%. The next question is asking, please evaluate the probability of obtaining the sample proportion like yours, assuming the claim of 15% defect rate is true. So I'm basically asking you to conduct a hypothesis testing based on this null hypothesis. Okay, based on this null hypothesis. You're assuming 0 is 15%. Therefore, the null hypothesis here is P0 is not equal to 0.15. Okay, and then of course our error tolerance alpha is going to be 0.05 as following the convention, and let's figure out the probability of obtaining sample size of this big or even bigger. Okay, so in this case, to visualize what we have so far on a normal curve, we have center P0, which is 0.15, and then we have obtained a sample outcome, let's say sample 1, okay, sample proportion of 1667. What is the probability of obtaining sample size of this size or even bigger? Okay, so when you draw a sample, your sample proportion is bigger than the hypothesized proportion. You want to obtain probability that is bigger than this particular value. If your sample proportion is smaller than the 15%, you're not looking for the probability that is less than that particular value. Okay, that is because the continuous nature of this probability, the probability on this particular dot is basically meaningless. The only way to making this meaningful is to obtain a probability of this size or bigger. Okay, so in order to understand this probability, of course, you need to find out your standard error. Okay, so your standard error in this case is going to be 1.5 multiply 1 minus 0.15 over 36, which is our sample size. So with this, we can calculate standard error here. Standard error, square root of 0.15 multiply 0.85, okay, divided by 36, close parenthesis, boom. So this is going to be your standard error in this case. Okay, so with that, all you need to do is to figure out the probability of obtaining sample proportion of this size or bigger using 1 minus norm dist. Remember, I'm doing 1 minus norm dist because it's beyond certain point concept. Okay, so your x is 16.67. Remember, this can be different for each one of you because we're drawing random sample. Okay, and then the center is 15%, and then the standard error is 0.0595, and then it's going to be true. Okay, so if you run this in Excel, and that will be the end of the problem. Okay, so excuse me, I'm not gonna finish this, but I think you will have pretty good understanding using this approach. Okay, so what is the conclusion? I can easily imagine this p-value of being larger than 0.25. Okay, 0.025. It's easily going to be bigger than 0.025. Therefore, in my case, I would not be able to reject my null hypothesis, which is basically saying 1.5. Okay, so remember, I'm not saying the population proportion is 15%. I'm only saying, based on my sample proportion, I don't think I can make a strong argument that says this is not true. Okay, because when you assume the the population proportion is 15%, drawing sample proportion like this is not gonna be very, very rare. It will be pretty common given the sample proportion is 15. Okay, so now you need to see two things. Number one, even we have completed all these processes, we still do not know what is the actual population proportion. Okay, number two, we were trying to attack a statement or a belief that we don't have, or we can never make a full understanding on that, what exactly that is going to be. But this is actually the second best way. I think this is only best way for us to evaluate how credible the claim about the population proportion 15%. Okay, if you have better way to find out whether the population proportion is 15%, please share with me. Okay, I'll make you my teacher. Of course, you need to assume that all these information are, of course, you need to realize that you can never study all the units that you are planning to study. It's just impossible. Sometimes it's just because too expensive. Sometimes it's just too time costly. It's too costly in terms of time, in terms of money. So it's never possible for you to study everything. Okay. But of course, this is our Excel data, and if you want to know what is the actual population proportion in this case, you can highlight column D, and average down bottom here shows you the actual proportion, which is 20%, 20.48%, which isn't exactly 15%. However, our conclusion, based on what we have done so far, we don't have any strong conclusion. We don't have any strong. We cannot make a strong argument to overturn initial a hypothesis, which is 15%. So if you don't like that, one thing you can do is you can actually using a larger sample size. I know this is not the part of the problem, but I'm gonna try this anyway. Okay, so what if I'm gonna use a sample size of 500? Okay, let's say that as a crazy sample. Okay, with a sample size of 500, you'll be getting incredibly small standard error. Okay, I'm just make that here. I'm going to draw the sample again. Data analysis, sampling, sample size of 500. Let's output this in here. Okay, and as you can see that here, average is 21.6. So I'm just going to put 21.6 and let us calculate the standard error again. Square root of this value multiply 1 minus this value. Okay, let's divide it with a 500. Okay, now because we have increased our sample size to 500, you see that our standard error is much, much smaller. So if I go back, if I give you an illustration, so let's say this is original sampling distribution when we use sample size of 36, okay? And this is new sampling distribution when we use a sample size of 500. Okay, as you can see, this is more skinny. The previous one is actually wider. That means sample proportion, when you're using sample size of 500, it's going to be more reliable because it's going to be fluctuating. It's going to be fluctuating within very short span, short interval, when compared to the previous occasion. Okay, so we can still do the testing. We're assuming it is 15%. We're still assuming 15%. And I think our sample is 21.6. Our sample proportion, let's say crazy proportion, crazy sample, 1/6. Okay, and then our standard error for crazy sample is 1/A4. Okay, so you can almost certainly guess that this is going to be leading to a rejection decision, because it's gonna be, it's gonna be here, very far away, right? 1/6, and standard error is this small. So let me in fact calculate this probability, okay, to see what different conclusion we can get here. Okay, p-value 1 minus 1 dist, and this is our sample proportion, okay, and our mean is again 15%, which is our hypothesis, and standard error is going to be this. We're going to use true. Okay, you see, p-value is near 0. So in this case, we were able to successfully reject our null hypothesis. Okay, how come? Let me maybe finish this. Okay, norm dist, and this is our x. Let's see. Boom. So how come you will be arriving in two different conclusions when you're drawing the sample from the same population? I mean, as you can see that we have used sample size that is much larger. Okay, so let me sample size. In this case, we use the 36, we use the 500. So because sample size is different, you see a very different standard error. Okay, and this is more sensitive in a sense. They will give you more close to true population proportion because of the property sampling proportion. Okay, so I hope I provided some more information regarding the first problem, and as well as your understanding about the sampling proportion. With that, I'm going to move on to the next question. So this is Maggie's data. This is Maggie's data. And if I were you, what I'm going to do is, for the convenience, I'm going to hide all this irrelevant information, because eventually you're only going to need E and I column. Okay, and this is index. We don't even really need that, so I can also hide that. I'm not deleting it. I'm just hiding it. Okay, later you can unhide it, so it will show up again. And let's take a look. So the first one is compare mean price length. So this is basically the t-test scenario. Okay, this is a t-test. T-test is testing the mean difference. Again, we need to figure out what is the null hypothesis. In this case, we're assuming both locations have the same length price. Or if you write it again, if you rearrange it, this can be another form of this. In other words, we're hypothesizing the mean difference of 0. Okay, so with that, I'm going to just quickly jump into the t-test Excel, because most of you don't have any problem with this. Go to here, t-testing, unequal variance. Okay, that is most conservative testing. For the range, I'm going to do so. Quickly jumping to the last observation of the location 1 is, once you click this and then Control-Shift, downward arrow. Okay, because there is empty space, so that action is gonna stop when it encounters a empty space, the blank space. And then for the second range, do the same thing. Control-Shift, downward arrow, and both area has been selected. We hypothesize the mean difference of 0, and we don't have any label, so let's output the result in maybe K1. Boom. Let's go back, Control, upward arrow. So this is your conclusion. Again, it does not show you what is the mean difference. It only shows you whether the mean difference is statistically significant or not. Okay, so if you look at here, the mean difference is basically here. Or if you have done it this way, subtracting second from the first, you'll be getting negative, okay, which really doesn't matter in this case. So our two-tail test is showing us the probability of obtaining this big of sample difference, assuming that the population mean difference is 0, is very, very small at 0.004 graphically. Again, we're using sampling distribution of population mean difference. Okay, this is a distribution that has been grounded on all the potential sample differences. So I explained that in a greater detail during the class. I'm just going to skip that part. So here is our difference. Let me just use a D to denote it, 0. And of course, you also need a standard error here in this case, but t-testing in Excel skip this part, so you don't really need to know. P-value says 0.003. Was it 3 or 4? 4. Okay, it was 4. So what it really says is when you're hypothesizing, when you're assuming, you're hypothesizing, you're believing the mean difference is 0, but you have obtained a sample mean difference, okay, that's a sample mean difference, 3. Okay, the chance of getting this sample mean difference or bigger is less than actually 1%, less than 0.1% even. It's very small, it's very rare. Therefore, it is very unlikely that the mean difference is not going to be 0. Okay, so your evidence is contradicting strongly, aggressively, with a pre-framed idea of population mean difference of 0. So it's not compatible with your hypothesis. The type of result that we have got using the sample is not compatible with your original hypothesis. Okay, that naturally, right? If you're thinking in that direction, the only conclusion we can draw is we need to reject our null hypothesis. Therefore, the difference may not be 0. Okay, but what is the actual mean difference? The t-test does not tell you. This does not tell you that information. It will only tell you what is the probability of getting sample mean difference of this. Okay, so with that, I think we're done with t-testing here. Please comment on your result. Establish a statistical significance. Again, this is basically a different way of saying what is the probability of obtaining that kind of sample, okay? Which you saw that based on the t-test result. This is 0.004, okay? And then if the standard error of the sampling distribution of the mean difference is 1831, please construct 95% confidence interval and explain what it is and what it means. For the B, earlier I made a comment that t-testing doesn't really tell you what exactly is the population mean difference here. Okay, so the t-test does not really tell you that, but we have another technique called a confidence interval that give you a potential range of the true population mean difference based on the sample mean difference you have obtained here. Okay, that is what confidence interval is about. Again, confidence interval is your prediction of where the true population mean difference is going to be residing, but you're only providing it using a range. Let me say it again. The confidence interval is a interval where you believe the true population mean difference is going to be residing with certain probability. So I'm asking you to draw 95% interval. So you'll be based on this mean difference to construct a interval here, and you believe that the true mean difference, if it's not 0, the true mean difference will be somewhere between this confidence interval. Okay, I think you can phrase this better than I did. Okay, that is basically what the confidence interval is. You construct an interval based on the sample mean difference you have obtained through your sample. Then you construct an interval surrounding that particular value. You construct an interval and you believe that the true population mean difference is going to be residing within this interval with a certain probability. Okay, so the confidence interval is, in this case, the mean difference you have obtained plus minus t alpha over 2 multiplied with square root n sample standard deviation. So this part, okay, this part is actually the standard error I already provided to you, okay, because this standard error for population, the standard error for the sampling distribution of population mean difference is very, very sophisticated. Okay, this is a generic version of the confidence interval when the standard deviation is not known, but you can just simply put plus minus t alpha over 2 multiply the standard error provided in the problem description. So I know why you're using t, not z. That's because the population standard deviation is not known. Okay, but again, the good thing is because we have large enough sample for this, you can safely using z, because when sample size is large enough, z and t are basically the same. So again, multiply standard error, that will give you a confidence interval. Okay, so I'm not gonna excuse me, not going to finalize the calculation here, but I think you get the idea. So because alpha is 0.05, you'll get 1.96 here. Okay, standard error, that will give you an interval. So no matter what value you have obtained, the interpretation of that confidence interval is that you believe that 95% of the time the true population mean difference is within this particular confidence interval. Or you can say, I have 95% confidence that true population mean difference is within the confidence interval. Remember, you still have 5% chance that are wrong, okay? But we're talking about 95% confidence level, okay? And the problem C is doing population proportion difference. It's not population mean difference, population proportion difference. So for that reason, we need to use this conforming, non-conforming data. I assume that this non-conforming means this is a defect, and 0 means this is okay. Okay, so let's say proportion defect for location 1. We also have proportion defect for location 2. Okay, quickly, this is going to be the average of this range, and then the other one is the average of the other part. Oh, there's a lot. Okay, here we go. Okay, then let's jump back. So now you have location 1 proportion this, location 2 proportion of this. So again, here difference in terms of proportion is I'm subtracting in this order, so I got a negative value. Okay, and of course we also need standard error for the population proportion difference, and which you need to rely on. Oops, internet error. This particular formula. I know this can be really involving in terms of calculating it. Let me just put it here. Oops, where is it? Yeah. Oh. Okay, it's finally here. When the equation is long, you can actually, decompose it and do it step by step. Okay, so I'm gonna do variance for location 1, variance for location 2 in this order. Variance is P1. P1 multiply 1 minus P, and I like to be safe and putting the parentheses everywhere. And the sample size, you can do count this part. Okay, so it will give you number of numerical observations here. And another one, square root of multiply 1 minus that, close parenthesis, divided by count okay. I shouldn't do the square root here, right? I shouldn't do the square root here. I'll do the square root later, eventually, after I add these two items up. Okay, now it looks more reasonable. And then square roots, this guy plus this guy. Okay. So after you got these two parameters here, everything remaining will be the same. Okay, you're basically doing the hypothesis testing or getting the p-value, assuming the difference in the proportion is 0. Okay, what is the probability of obtaining sample proportion you have obtained, which was negative 0.005. Sorry, negative 0.005-ish. Okay, and then the standard error was 0.34. Okay, so I think it's fairly close to the average given the standard error. Okay, so you can figure out what is the probability here. So because this is the only left-hand side, you can easily using the norm dist to figure this thing out. Okay, norm dist. Your sample proportion difference is this. You're hypothesizing 0 difference, and your standard error is 0.34. True. Okay, I think you'll be getting a fairly large proportion here, so you'll be probably getting a p-value that is larger than the alpha over 2. Remember, this is testing the equality, therefore it's a two-tailed test. Okay, so you'll be getting a p-value that's much larger than 0.025. Therefore, you cannot reject the null hypothesis. So the best thing you can say is that I don't have enough information. I'm sorry, I don't have, or my sample proportion difference is not strong enough to reject the null hypothesis. Okay, so your best option is to accept the null hypothesis as true. So you're accepting it as a true, not because it is a true, because there's no way to disprove that is not true. Okay, sorry if that made you confused. Okay, but that's basically what it is. Then question number D is basically, it's very, very simple. It looks scary, but question number D, if you have paid attention during the class, this is actually very, very simple one. You don't even have to do any calculation here, right? Bx. So here, x can be between 0 and 1, right? And B, in case of two mean difference, in case of two population mean difference, B is basically the mean difference, okay, mean difference. Therefore, B follows a sampling distribution of population mean difference. Okay, so when we convert it, when we try to apply it for the population proportion difference, it's the same. The B here, I mean x is the same, right? In the same manner, it only can take between 0 and 1, such that when it is 0, we are talking about the population proportion for the first group, and when it is 1, we're talking about second population proportion. Okay, so B is going to be the population proportion difference. So therefore, B is also following the sampling distribution of population proportion difference. Okay, it's following the sampling distribution of population proportion difference. Okay, that's it. So that is going to be your solution for the D. I think I'm asking something more specific. It's shape, center, and the variability. Because we don't have a true knowledge for the center, so you can just say the center of that distribution is a true difference between two populations. You can just say it that way. Okay, I hope you understand what that means. The center of that sampling distribution is a true difference of two populations, regardless if it's a mean or proportion. Okay, so you can just write it up verbally, and that will be it. Now it's number 3. Here is a two-way ANOVA. You can just go here and jump. Two-way ANOVA without weight replications. So highlight these. Okay, and there are 3 observations per row, but I'll put it somewhere here. With this, we have a lot of information here. For the sample, I'm just going to say it's a GlassType. And for the column, it's actually the temperature. Okay, it's temperature. So with that, we have ANOVA result listed here. So what is the amount of total variations that can be explained by these two factors? So I expect you to understand what this is. Whenever I say the amount of total variations, so the amount of total variations is actually here, sum square total. Okay, sum square total. You may recall during the class I showed you how to calculate the sum square total. So here is the detailed steps here to how to calculate the sum square total. Okay, this is basically a quantified measure of overall variations. This is not an average variance. It's not an average variations. This is just overall variations. Okay, and then let's go to the next question. Amount of variations that can be explained by these two factors as well as the interactions. So again, if you look at here, this is our total variations. This is our SSE. Okay, this is our SST. Okay, GlassType explained this much proportion of variations. Temperature explained this much. Interaction explained this much variations. So out of these variations, SSE over SST, SSTR over SST. So amount of variation that has not been explained is this much here. And then amount of variation that has been explained is actually sum of all three divided by the sum square total. Okay, or we can just do 1 minus sum square error. I'm sorry, 1 minus sum square error proportion. So that will basically give you the same result. So what this means is that among the total variations, okay, we're trying to figure out what is causing all these differences among our observations. Why some people are 6 feet, why some people are 5 feet and 4. What is causing all these differences in terms of those response values? Okay, so in our case, we're trying to explain the difference between variations among the thickness of the glass. So you can see that glass type is contributing certain portion to that difference. Temperature is also contributing to that variations, and so is their interactions. Okay, and also judging from the p-value, all these are statistically significant factors. Okay, so all three combined, they're contributing near 100%, only less than 1% variations that are not being explained. So basically, I think we know everything about what is causing the variations in our response variable. Okay, we only do know very little, but it's really, really low. Okay, so you can basically in this case say we know everything about this phenomena. Okay, so that is basically what how your interpretation should follow. Again, I said all the factors are introducing significant variations. Please plot the interaction and paste it here and offer some explanations. So to do that, you need to be able to read. Okay, be able to read this portion of your data. Did I do everything? Oh, okay. That's okay. You can do it yourself. When you do the homework, you actually need to eliminate the group that I told you to eliminate. Okay, but anyway, so for the next illustration, I'm only going to be using these four treatments because the 3x3 is going to be a whole lot more difficult to plot than 2x2. Okay, so we're talking about 9 treatment group cannot present it in a 2-dimensional chart. So let me just offer the interaction using these 4 treatments. You should have your own 4 different treatment groups. You can use your own. Let's see how it works. Okay. For that, you need to go to plot it, to go to textbook data, and you have 2x2 factorial experiment. All right, let's take a look. So, side by side, our first factor is temperature. No, it's glass type. Next one is temperature. Okay, and glass type 1, glass type 2, and temperature 100, temperature 125. Remember, I think yours is going to be different here, okay? I think you need to do temperature 100 with temperature 150. And let's put the low, which is the low treatment, which is glass type 1 with a temperature 100 average. 100 average, which is this value right here. And high-low, okay, high-low, factor 1 high, 2 100, 2 and 100, 2, right, 2 here and 100 here. So this is going to be your average. And low high, glass type 1, 125. And high, is last group. Boom. So this is what I have here. It looks like the main effect is very little compared to the main effect for the factor 1 is very little. Okay? Main effect for the factor 2 is actually very large. And interaction is also very, very small. Again, you will be looking at different graph because you're using different treatment groups for your homework. Okay, as you move, the interpretation is for when you change your class type from 1 to 2, you don't see much increase or decrease. You see actually slight decrease in terms of output. Okay, you see you see that both group they decrease very little. They decrease a little bit. Okay, so overall, our main effect when you move from glass type 1 to glass type 2, regardless of which temperature you're using, it's negative 36. For the factor 2, when you switch from factor 2 low to factor 2 high, we see a big increase here. Okay, regardless of the glass type, when you increase the temperature from 100 to 125, you see that it has increased. Also for the interaction, this interaction is actually very, very small. I explained that for the interaction, you need to identify the slope difference. Okay, so there is a slight slope difference. I don't think that is huge, but what does it say about your experimental condition choice decision? If you want to design an experiment, if you'd like to create an environment where you can obtain the maximum output on your response variable, because there is a slight interaction, you want to use what? You want to use the experiment condition that will give you the maximum outcome, which in our case is a combination of factor 2 high, okay, factor 2 high with factor 1 low. Factor 2 high, factor 1 low, which is what? You'll be using this combination. Glass type 1 with a temperature high. Okay, that will give you bigger output, the biggest output. That is basically what you can say from the interaction. Again, if you visit the question E, how does it help you making making the temperature and glass type choice? Again, like I said, to have a maximum output or outcome, you want to choose temperature high with glass type low. Okay, so that will basically conclude this particular part. But if you think it was not enough to help you understand what interaction is actually about, so let me use this another example to quickly illustrate what the interaction is. So again, here is low, here is high. Okay, to help you understand better, I'm going to be using example that we're all familiar, the Kroger. Okay, so the y-axis here is going to be the cells. Low, high in terms of, let's say, uncertain business environment. Okay, uncertain business environment. So when it is low, it means there's very low uncertainty. When it is high, it means there's high uncertainty. Okay, like COVID-19 is a typical classic example of high uncertainty business environment. Factor 2 is level of e-commerce. Level of e-commerce in their purchasing process. Okay, like Kroger, they do click list. You order online, pick up offline. Okay, that is the high level, right? You can have a low, you can have high. So you can imagine some local mom and pop store, they don't usually have an e-commerce. Okay, so you can consider those as a low e-commerce group. For Kroger, those larger business, you can consider have high level of e-commerce during the purchasing process. So when in the old times when there's no e-commerce, right? And then there's very low uncertainty in the business environment. Let's assume this is your sales level. Okay, let's say 100 here. Okay, when the environment turns very turbulent, like during the COVID-19 time, you'll typically see a sales drop like this. Okay, so this is actually for the low e-commerce group. Low e-commerce group. So when business environment turns uncertain, their sales drops. Okay, is that the case for the high e-commerce? So let's assume that typically the bigger store have bigger sales because they have e-commerce, right? So let's say their sales is 200. Okay, if let's say there is no interaction exists between the uncertain business environment with the level of e-commerce, you probably expect the same level of drop here in terms of your sales. However, if you do expect an interaction here, you actually have to draw something different. Okay, so I'm going to draw something like this. So think about during the COVID-19 when you cannot make a purchase from the typical grocery stores, you all go to the venue you believe it is safe, okay? Which in this case, you typically are willing to order online and go pick it up from the offline. That actually increases sales of your e-commerce owners. Okay, so because of the interaction, what you can tell from this example is you can ask questions such as, does e-commerce really matters? Okay, does e-commerce really matters? If you look at this output, this experiment actually favors this particular combination. Okay, in fact, they're enjoying business environment that is uncertain. Okay, this treatment, high in e-commerce, and also high in business uncertainty. This actually turns out to be very, very good in terms of their sales. So now you see interaction here. There's different slope, and there's also story. So the conclusion here is, if possible, let's implement e-commerce here. Okay, it helps either way. Okay, it helps either way. So that's usually what interaction is all about. It tells you different slope, and it also tells you which particular treatment is being favored by this experiment. Okay, I think that is it. I've been explaining, go on and on for an hour. I think you have enough information to complete this homework assignment, and I will stop here. Okay, thank you.